Dear friends, Maths Aspirants is a collective of mathematics students, research scholars, and faculty members across India initiated by myself in 2017. Apart from providing a discussion platform for math lovers, we used to arrange online problem solving sessions and online test series to help the students who prepare for different national level competitive examinations like IIT, JAM, CSER, NET, GATE, NBHM, etc. As a part of that series, today we blessed to have Dr. Saranya Ji Nair is with us to engage a session on sequences and series. I would like to appreciate Dr. Saranya for being with us. Actually, for faculty members, they usually prefer to engage theoretical sessions. Uh, but I told her that as this year's JAM examination, gate examinations are very near, so it will be very nice if you can problem solving session. So anyway, she wholeheartedly accepted my request and agreed to do this session. So let me introduce Dr. Saranya. Dr. Saranya is currently an assistant professor in or assistant professor of mathematics in BITS Pilani, Goa campus. She did her MSc from Cochin University of Science and Technology, and she secured PhD from IIT Bombay, and her broad research area is number theory. So today she will discuss some problems related with series. I am sure that all of you will be really benefited out of that session. So to welcome everyone to this program. Welcome, Saranya.
Thank you, sir. Thank you for having me here. So I understand that there will be challenges that I have to face today in the sense that I don't know the audience. Like the audience is a big collection. It is they're from diverse background. So I'm planning to make it interactive. Yes, as sir mentioned, theory, we are more interested in doing the theory because it's true that if you understand the theory, you will be able to be more comfortable in applying it to the problems. So I have chosen some problems in such a way that I can also mention the theory along with that. And so it should be more enjoyable. Like it should not be that we are doing one problem and there is a pattern and we just follow the pattern. Because as I understand that you are all interested to pursue mathematics in your further like MSc and maybe further for PhD and all. So I faced the challenge, like I was also a math student, a degree student earlier. So what the challenge I faced initially when I was going into the research direction was that maybe while doing the problems, or we really need to focus a little more into the theory. Like we cannot forget the theory when we are doing the problems. So so the problems I have chosen are also in such a way that I can also tell you a little bit about the theory. So I hope that will be fine. So let's begin with sequence. So we all know the definition of sequence. So we are considering sequence of real numbers. So sequence of real numbers. So by sequence, what we mean, we have a function from the set of natural numbers to real numbers. So one is going to, so if I denote my sequence to be an, one is going to a1, then 2 is going to a2, and so on. So the moment we call something sequence, what it indicates that we are associating each term of the sequence with a natural number. So that is what even our notation indicates. An means it is a1, a2, a3, and so on. So say, for example, the set of all students who have joined in this class. So can I write it as a sequence? Yes, I can, but it's going to be finite number of students. So what I can do is either I can write a constant sequence using this finite number of sequence, or what I can do is I can call the first person as A1, second person. Maybe I can do an ordering either with the roll number or with the alphabets. And then I can call the first person as A1, A2, A3, and so on. And then A45. And when I come to A46, since this is a function from natural numbers, and this is an infinite set, so I need to tell what will be A for any K from the natural number. So now again I have to define what is A46. Either from A46 onwards I can define it to be 0 or any number, or I can again come back to A1 and call that A46 is A1 and then do this process. So we can have lots of example for sequence. And so what do you mean by a sequence converging to a limit? I'll just write the definition so that in between some problems we may need to recall the definition. So what do you mean by a sequence AN is converging to L? So this means for every epsilon greater than 0, there exists an N in the set of natural numbers such that the difference between AN and AL, the sequence terms are denoted by AN. So I'm looking at the difference between AN and L. This I'm able to make it as small as possible. Now the question is this going to be true for every term in the sequence? It may not be. Maybe the first few terms I'm not able to make this relation depending upon the epsilon I'm choosing. But I'm sure that if AN is converging to L, after a stage, I'll be able to get this inequality. So that stage only I have written as N in terms in the beginning. So this is going to be true for all N greater than or equal to N. So this is what we say, but what you meant by a sequence AN is converging to L. So with this definition, you also know that what you meant by subsequence. So I'm not going to tell the definition of everything. I'm just recalling what are the things you may be knowing in the sequence. So once you know sequence, you will be knowing subsequence. Then you will be talking about, so convergence you have already told. Convergence you have already told. What you meant by a sequence is convergent. And then you can talk what you meant by sequence is divergent. So a sequence diverges means, so whatever M that you are choosing, whatever real number M that you are choosing, so mod AN will be greater than M for all N greater than or equal to some stage N. So this is what we meant by sequence is diverging. And then you have the concept of a sequence being monotone increasing or monotonically decreasing. And then subsequence we have already told. So I think with this terms, we can look at the problems in sequence. And we'll see in the order when it comes if we need to explain something more. Okay. So let's look at the first problem. I'm giving a sequence xn equal 1 divided by. Okay, so obvious example for sequence that you would have already seen is 1 by n square, then n sin n, anything. So you know a lot of examples. So let's look at this. 1 divided by 1 plus n square plus 2 divided by 2 plus n square, etc. plus n divided by n plus n square. So this xn is given. I have to see whether the sequence xn is convergent or divergent. Yeah. So what I am able to see here is that the xn, the nth term of the sequence itself is a sum of some n number of terms. So if I am able to talk about this sum, then I'll be able to talk about what is this xn. Normally in this xn equal to 1 by n, you were able to see that nth term as, this was more simple form, but this is now, this is sum of more number of terms. So I need to really see what is the sum or how or what can I give a bound for this sum first of all. So let's look at the terms in this, each of these terms. The first term is 1 by 1 plus n square. And second term is 2 by 2 plus n square. And the last term in the sum is n by n plus n square. The question is, if I look at the denominator, so denominator of each term, first term is 1 by 1 plus n square. Denominator of the second term in this sum is 1 by 2 plus n square. And denominator of the last term is 1 by n plus n square. So if I can compare the terms 1 by 1 plus n square, 1 by 2 plus n square, and up to 1 by n plus n square, then comparison will tell me how big this sum is going to be or how small I can make this sum. So you see that whenever we do analysis, this kind of comparison will be coming more often. We're always interested to compare a given expression with a non-expression. The non-expression in the sense that we know how the non-expression is going to be, whether it is bounded or whether it is converging or diverging. So based on that, we're always interested to look at bounds like this, say lower bound or upper bound. So if I look at each term here, I can clearly see that all these terms here. So if I look at any integer k plus n square and compare it with n plus n square, now I'm taking an integer k and I should also write where is this k ranging from. So I'm writing k is ranging from 1, 2 up to n. So for these values of k, what do I know about k plus n square and n plus n square? I know that this is less than or equal to n plus n square. Why I wrote equal to? Because if I take k equal to n, n plus n square can also come. If I would not have taken n, then I could have put a strict inequality here. So this much I know. So that means each of this term 1 by 1 plus n square. So I can write here 1 by 1 plus n square. This is greater than 1 by n plus n square. Then 1 by 2 plus n square is also greater than 1 by n plus n square. So like that, the last term I'm going to put this equality. So ultimately what I'm getting is each of this sum, I'm able to give a lower bound in terms of this 1 by n plus n square. So let's write that. So I'm writing a lower bound here. 1 by 1 plus n square plus 2 by, so everything I'm replacing by n plus n square. So n by n plus n square, etc. plus n divided by n plus n square. So this is less than xn. Now on the other hand, I can also give a upper bound. So how does the upper bound now look like? Now I know that. So each of this term, 2 plus n square is bigger than 1 plus n square. So 1 by 1 plus n square will be less than 1 by 2 plus n square. So I'm using that. So 1 by 1 plus n square plus 2 divided by 1 plus n square, etc. plus n divided by 1 plus n square. So now this side, the denominator is 1 by n plus n square and the sum is 1 plus 2 plus etc. plus n. So I know that this can be written as n into n plus 1 by 2 into n into 1 plus n on the other hand. And this side I can write it as n into n plus 1 by 2 into, again this 1 plus n square is here. Okay. So what I am getting is a bound like this. So now we have successively able to put our terms. We have given a lower bound for the term xn and an upper bound for the term xn. And we can now consider this as a sequence and this as another sequence. So this sequence I am calling it to be an and this sequence I am calling it to be bn. So suppose I know where does an converge to and where does bn converge to, then I can use the fact to talk about the convergence of xn. So suppose I know that an is converging to a limit L and if bn is also converging to a limit L, and then I can tell that xn will also converge to the same limit L. So let's see what is the convergence for an and bn that you are getting. So this is clear that an is converging to half. Similarly, bn is also converging to half. So what I am using is sandwich theorem. So by sandwich theorem, now I know that xn will also converge to half. So essentially, what is sandwich theorem? Using the fact that if you have two sequences xn and yn, such that xn is greater than or equal to yn, then what happens when you take limit of xn and limit of yn? Do you still have this order relation when you take the limits? Yes, you have. And from here only, we are able to prove this sandwich theorem, which we have been able to successfully apply in this theorem to show that yes, xn is also converging to half. So this is where theory is going to be helpful. You look at a sequence with some property when it compared with the other sequence, and then you showed that the limit of xn is also greater than or equal to limit of yn. So this will, if you want to show this, we may need to look at some arguments. But once you show this, you're able to use it in your problems very easily. Okay. Now, let's look at another problem. So let xn equal to a raised to n plus b raised to n the whole raised to 1 by n, where, so I'm talking about a and b. So everything here, n is there. So n is here. Only thing which is different from n is no a and b. So I should specifically tell what is this a and b, or from where do they belong to, or can I define, or can I give more specification about from where I am taking these values of a and b. So I'm writing here a should be less than or equal to b. Also, I am telling that I also want a to be greater than 0. So this is my sequence xn. Now I want to show where is xn converging to. Where does xn converging to? So again, so what I'm going to use here is the fact that the limit n tends to infinity, n raised to 1 by n equal to 1. So this I'm assuming that you know and you have already did this. So let's try to use this here. So again, I'm trying to see if I can give some expression so that xn is given. I'm looking for a bounds for xn in the terms of lower bound and upper bound. So as in the case earlier, if I can give that lower bound and upper bound, and if I know they are going to the same limit, I can apply the sandwich theorem. So let's try to do it in the same way. So we know that b, I can write it as b raised to n the whole raised to 1 by n. This is true. And why I'm writing here? Because this b raised to n is here. So I need to, so an plus b raised to n, since a is less than or equal to b, I know that I am able to write this is less than or equal to 2 times b raised to n. Therefore, xn will be less than or equal to 2b raised to n the whole raised to 1 by n. So upper bound is easily got. Now a lower bound, this is a lower bound because I am taking a to b. So what I used here was an upper bound of a, which is given by b. Similarly, I also know a lower bound for a here, which is given by 0. So I'm using that lower bound to tell that, so this is going to be less than my xn, which is less than or equal to 2 times bn the whole raised to 1 by n. And now I know, by applying this, I know that this sequence will go to 1. And now I also know that this is bn the whole raised to, this is, no, I didn't have to use this here because b is a constant number. So this is just b. So this is b raised to n raised to 1 by n. So you are getting here, this is b, right? This is not going to 1, this is going to b. So b less than or equal to xn. Now again, what I'm getting here is this is less than or equal to 2 raised to 1 by n into b. Now here I am applying my limit that this is going to, so you know that now xn will convert to b. Okay. So then, so what do I do here? I did not have to use this in the full term. What I actually used is limit n tends to infinity, 2 raised to 1 by n is also 1. Okay. So now let's look at another problem. So sandwich theorem is quite useful. Only thing is that using that, we may be now able to look at more and more difficult sequences. And the difficult in the sense that the expressions will be slightly more complicated. Yeah. So now the way it is written, it's clear that I can compare the terms like in the first problem. So this first term and the last term. So I can see that I'm actually comparing 2 raised to 1 by 3 with 2 raised to 1 by 2 and plus 1. So whenever you are doing this comparison, just be careful initially so that the upper bound and lower bound is being taken correctly. Like maybe when you do it sometimes, maybe out of hurry, you may be making some mistake and then less than will become greater than n. So be careful when you do this inequalities for some time. So 2 raised to 1 by 3. So what I am actually doing here is I'm comparing 1 by 3 and 1 by 2 and plus 1, which I am able to compare because I can compare this fixed integer with an integer of the form 2n plus 1 because n is anyway going to infinity. So this I know, this is bigger. So hence this is bigger. Hence I know that root 2 minus 2 raised to 1 by 3. So I'm taking the minus. So I know that this is going to be less than root 2 minus 2 raised to 1 by 2 n plus 1. Similarly, I can use this for other terms. This is also less than root 2 minus 2 raised to 1 by 2 n plus 1 and so on. So I'm readily getting a upper bound here. So xn is less than or equal to root 2 minus 2 raised to 1 by 2 n plus 1, the whole raised to. Now here n terms are there. So I have gone up to here 2n plus 1. That means there are n such terms. So I have here n. On the other hand, what could be a lower bound I can use here? So I can see that 2 raised to 1 by 3, 2 raised to 1 by 5, up to 2 raised to 1 by 2 n plus 1. I know that this is the limit. This is going to be 1, the 2 raised to 1 by n4. And root 2 is bigger than 1. So each of these terms are greater than 0 that I know. So that I am able to use here, tell that, yeah, these are all greater than or equal to 0. Okay. Now, when I look at here, again, so here again I can apply that upper bound. So I'm able to now write this as root 2 minus 1, the whole raised to n. Now I am using the fact that limit n tends to infinity. So I know this fellow is constant sequence 0 going to 0. Now you should know where is this sequence going to. But I already know that limit n tends to infinity r raised to n. So if you know that if you're taking r to be less than 1, this is will also going to 0. So we only need to ensure that the r value that we are taking is actually less than 1, which is true because I know that root 2 minus 1 is less than 1. Okay. Yeah. So again, by sandwich theorem, I'm able to show that xn is converging to 0. So in this problem, we are actually combining sandwich theorem with other non-existing limits, because anyway, once you provide the inequalities, you should know where is this sequence going to and where is this sequence going to. Okay, now next problem. So this is xn equal to n raised to alpha minus n plus 1 raised to alpha. Now again, n, I know how does n behave. Now there is a new term here, alpha. So I should describe where is this alpha or what is this alpha going to do here. So I'm telling alpha I'm taking to be any alpha. So for some alpha, which is lying between 0 and 1, strictly lying between 0 and 1. So that means if you are taking alpha equal to half, I'll get a sequence xn equal to n raised to half minus n plus 1 raised to half. If somebody else is taking alpha to be 3 by 4, they will get another sequence n raised to 3 by 4 minus n plus 1 raised to 3 by 4. So irrespective of the choice of alpha, when alpha is lying between 0 and 1, we want to see what happens to the sequence xn. Can you say that this sequence is having a common limit? Let's see how does that work. So what I'm, again, this is going to be comparing, like we were being comparing different terms. So here also, I'm going to compare this n raised to alpha with n plus 1 raised to alpha. So you can see that, so I can write my xn to be, I'm trying to take this n raised to alpha outside. This is 1 minus 1 plus 1 by n, this raised to alpha. So you can see that if I would have taken minus xn, it's easy for me to compare, because then this 1 minus 1 plus 1 by n and all I can remove here. So what you can see here is that this 1 plus 1 by n raised to alpha. The term here, the minus of that, and then minus 1. I am taking the minus of this because I'm looking at minus xn. So this is n raised to alpha into 1 plus 1 by n the whole raised to alpha. This minus 1. Now this is less than 1 plus. Now I am using the fact that alpha is less than 1. So this is less than 1 plus 1 by n minus 1, which is actually 1 by n. So I know that this is less than or equal to n raised to alpha into 1 by n, which is n raised to So alpha minus 1, or I can write it as, since I know that alpha is less than 1, I'm writing it as 1 by n raised to 1 minus alpha. Now, I need to see what happens to this sequence. So on the other hand, now I'm looking at minus xn. So minus xn. So what do I know about minus xn? Minus xn is n raised to alpha into something. So this is greater than or equal to 0, I know. Right. On the other hand, this is less than or equal to this. And now again, alpha is a fixed number. So this is 1 by n raised to a positive power of n. And you know that as n tends to infinity, n raised to this will go to infinity. So 1 by that will go to 0. So this fellow will go to 0. So I'm able to show that minus xn is converging to 0. So this will imply that xn is also converging to 0. So what actually I have used here is that if you know a sequence xn is converging to L, then what do you know about a constant times that sequence? So if I look at the sequence yn, and if I write it as c times xn, so this is my another sequence I am defining. This is also a sequence. And can I tell that this is going to c times L? Okay. So once you know the theory, you are able to apply it. But when you are looking at the theory, you know that how do we prove this? If xn is converging to L and if cxn is converging to Cl, how do you actually prove this? You need to come to the epsilon definition and show that, yes, my C times xn minus Cl, also I am able to make their difference as small as possible. Whenever the difference of xn and L, I am able to make as small as possible. Okay, so once you prove that, you are able to use this. So similarly, what do I know? I also know that if xn is converging to L, and if say yn is another sequence which is converging to k, then xn plus yn is converging to L plus k, and xn minus yn is converging to L minus k. So I know that you will be knowing all these things, but the thing I want to emphasize here that you please go back and look at the proof of this also. Like how you are choosing your, see, whenever you want to apply this definition, xn is converging to L, the key thing is that whenever you choose the difference epsilon, you want to find what is the stage that you are looking for. So if you know a stage where xn is converging to L and yn is converging to k, what is the stage that you need to choose so that xn plus yn will converge to L plus k? So if you write the proof by yourself, you'll be able to understand that what is that minute things that how you need to be taking care so that you are able to get the ultimate result. And this minute observations only, this kind of observation only we actually need when we are pursuing higher mathematics. Okay, so next one, another question, xn equal to 2 raised to n by n factorial. Yeah, so this, when I'm just comparing the numerator and denominator, both numerator and denominator are actually going to infinity, right? This is this 2 raised to n is also going to infinity. N factorial is also going to infinity. Moreover, I know that n factorial is actually like this n raised to n, or there is this Stirling's approximation formula for n factorial, Stirling's, where you are actually able to give a upper bound and lower bound for n factorial in terms of some function in terms of n, which involves e and all, and n raised to n. Similarly, here also an n raised to n into some other function in terms of n, which involves exponential function and all. But the importance is that there is a lower bound for n factorial and upper bound for n factorial, which is given in terms of a function where n raised to n is also a part of the function. Okay. So if you want to directly compare this terms of the sequence, you know that there is going to be difficulty. So what actually now you can do here is that, you know, there is a ratio test for series. So similarly, there is a ratio test for sequence also. I won't give a proof for that. So what is this ratio test telling? So if you look at limit n tends to infinity, xn plus 1 divided by xn. So if this limit is less than 1, then you know that this sequence, where is the sequence converging to? Okay. So xn plus 1, you can tell that yes, this is converging. So xn plus 1 by xn. So if I, now once you know this, you can simply go and find what is its limit and check whether the limit is less than 1. And then you can tell that, yes, this xn is converging. Okay. So now let's move towards the next category of problem. Again, in the I'm just focusing little more on the sequence because so that when you know the sequence, series is going to be easy. So one more sequence, let's give. So 1 minus 2 plus 3 minus 4, etc. plus minus 1 raised to n minus 1 into n divided by n. So this is a sequence. So clearly, the terms here is depending upon what will be the sign of this minus 1 raised to n minus 1, which will in turn depend when n is odd and even. So we need to make that distinction here when if you want to look at the terms of the sequence. So what happens to the even terms of the sequence? And then what happens to the odd terms of the sequence? So you know that if a sequence converges, then every subsequence will also converge. So I'm actually seeing what happens to the odd sequence and even sequence. If they are itself going to different limits, I can directly tell that yes, the sequence is not converging. So if I look at x2n, so x2n means when n is, so this is minus, so this is 2n, so this is going to be odd. This is minus 1 raised to an odd number. So this is minus 1. So I can group these terms. When I group this, I'm getting a minus 1. Again, when I'm grouping this, I'm getting a minus 1. So when n you are taking to be even, I'm getting minus 1, 2n by 2 times, n times, then divided by whatever is the n. I'm taking n to be 2n here. So that 2n will come here. And then this, I know this is going to minus half. So what happens when n is odd? When n is odd, this is going to be plus. So before that, there is a minus. So all those minuses I may be able to group like earlier. So that will be minus 1 times and n is there because this is, now n is my 2n plus 1 odd, okay? So this minus 1 is 2n and then by 2 is n. That is why this n has come and then minus 1 is there. So minus 1 into n plus whatever is remaining, this is positive and that n is given by 2n plus 1 divide by this 2n plus 1. So this will give me n plus 1 by 2n plus 1 and this you can see that this is going to half. So I got a subsequence where the subsequence is converging to minus half and I got another subsequence where it is converging to half. Hence, the sequence cannot converge. So it diverges. So this is another definition of diverging. Like something not converging is also defined to be diverging. So there are two notions of divergence of a sequence. One in terms of not converging and another in terms of yes, it is diverging to plus or minus infinity. Okay. So now let xn be a sequence. Now the question is, if you know where is this xn converging to, if xn converges to 0 and yn is bounded sequence, then can you say that x and yn converging to 0? This is the question. So you know that earlier we saw that if you know the limit of two sequences, xn and yn, xn plus yn or xn minus yn, similarly product also we can tell. If xn is converging to L and yn is converging to k, you can show that x and yn is actually converging to the product Lk. The product sequence is having the limit to be, which is the product of the limits for the individual sequence. But here it is slightly different. We are telling that xn is converging to 0. I don't know about the convergence of yn, but it is given that yn is a bounded sequence. What do you mean by a sequence bounded? I know that I'm able to find a real number m such that I'm able to give a bound for this yn in terms of that m. So, or other way, I have this real line and there is this minus m and m over here. And I know that all the terms in my sequence are lying to be within this range given by minus m and m. This is meant by yn is bounded. So this is given to you. Now with this information about yn and because you know about xn going to 0, can you show that x and y is converging to 0? So if you want to show something is converging to 0 in terms of a general sequence, so earlier you were given what is the sequence pattern. So you could apply all these properties and see where it is converging to. Now you are only given a sequence which is general. Xn is any general sequence. So you need to come to the definition of how do you prove for the sequence convergent to show that yes, what happens or what is meant by the convergence here. So I want to talk about this, but I know that this is less than or equal to mod xn times mod yn. The mod yn I know it is given by this is less than or equal to m times mod xn. Now I know that xn is converging to 0. So I know that mod xn, I'm able to make it as small as possible. Okay. So I'm able to make this is less than epsilon for all m greater than or equal to some stage. So that means m times mod xn. This is also under my control. I'm able to make this as small as possible. And on the other hand, this lower bound is given in terms of 0. Okay. So this is going to 0. So again, by sandwich theorem, I'm able to conclude that x and y is going to 0. So now here, it is clear that this boundedness of yn is playing a role here. If you did not have this yn to be bounded, then you may not be able to talk about whether x and yn is converging to 0 or not. What is an example? If I take xn equal to 1 by n, I know that this is converging to 0. But if I take yn to be n, this is not a bounded sequence. And if you look at x and yn, yeah, this is converging to now 1. So this is not an issue. So, but if I look at it yn equal to n square, then here I will get x and yn is actually converging to n, and this is not converging to the number which is, or any number, it is not converging, it's diverging. So boundedness of yn has helped us to conclude about x and yn here. So another problem in the same direction. So these are small problems which you can practice, so that I have seen that some ways they will be giving 4 statements like, and you need to choose which of the following are correct. So such kind of statements can come here. So if xn is converging to infinity, or if xn is going to infinity and yn is a bounded sequence. Now same property about yn, but now xn is going to infinity. Earlier xn was going to 0. Then x and yn, the question is whether x and yn will also go to infinity, like what happens to this x and yn going to 0 in the earlier case. So here you can see that it need not be. So what you can give an example is xn equal to n, this is going to infinity, yn I am taking to be 1 by n, which is a bounded sequence. This is all less than or equal to 1. But x and yn not going to infinity. It's actually going to 1. Okay. Now another question in the same form. If you know about xn plus 1 by n xn, if this converges, then can you say that sequence xn converges? And what about the converse? If you know xn converges, can you say that xn plus 1 by n times xn converges? So let's see the if part first. So you are given that xn plus 1 by n xn converges. So let us take that as a sequence yn equal to xn plus 1 by n xn. So this I can write it as xn times, can take xn outside. So this. So I want to talk about xn. So I'm writing xn in terms of this yn. Yn divided by 1 plus 1 by n. So what do you know? This 1 plus 1 by n. 1 by n tends to 0. So 1 plus 1 by n is tending to 0. So what I am using here is, if you know a sequence an is converging to k and if bn is converging to l, then an by bn will converge to k by l, provided I know that I am taking bn's where it is non-zero terms in the sequence and the limit of bn is non-zero. Okay? And here the limit is non-zero, so I'm able to use this. So I know that since yn is converging, it is say it is converging to some l. So this is also converging to L. So Xn is also converging. Now, what about the converse? Suppose you know that Xn is converging. Okay. So if Xn is converging, converse, what can you say about? Can you say about the convergence of Xn by 1 by n Xn? So if you want to talk about the convergence of this, you need to look at least to begin with, you can see whether it is bounded, because we know that every convergence sequence is bounded. So if you can say it is not bounded, so at least boundedness you can first study. So I'm looking at the boundedness of this. So this is less than or equal to mod Xn plus 1 by n times mod Xn. Now 1 by n is going to 0, I know. 1 by n is going to 0. So this means I'm able to make this 1 by n as small as possible. But anyway, here I know that 1 by n is again strictly less than or equal to 1. So I can simply apply that here to get that 2 times this mod Xn. Now I know that Xn is converging. Hence, 2 mod Xn is also converging. Hence, I know that Xn plus 1 by n, this is also going to be converging. So I can talk about the convergence of this. Okay. Now another thing, so this is 4 from here. So what's the difference between this and earlier? So earlier I had only Xn plus 1 by n Xn. Now I have increased power here. This Xn square plus 1 by n Xn. So here, then will it Xn be converging? So here this need not be. So we have an example. If we take Xn to be minus 1 raised to n, then Xn square is going to be 1. So this is so what happens to Yn? So Yn is, so can you see that now Xn equal to minus 1 by raised to n? So this will always go to 1, but Xn is actually not converging. Okay? But this fellow is converging. Okay. So now, so we talked about, when we were talking about sequence, we talked about subsequence sandwich property. Now let's look at the monotonic sequence. So suppose I am giving you the sequence x1 equal to root 2, xn plus 1 equal to root 2 times xn. Okay. So now what can you tell about the convergence of xn, whether xn is converging or not? So when I look at x2, so x2 is how much? So x2 will be square root of 2 root 2. So this is going to be greater than x1. So I know that x2 is greater than x1. So can I show that xn plus 1 is greater than xn? Okay. If you can show this, then you can say that yes, it is monotonic increasing. So many times if you want to look for how do you show this is increasing? So one thing is to look at the difference directly, xn plus 1 minus xn, and show that this is greater than 0. Another thing is look at it as a function in terms of n. See, xn plus 1 and xn are in terms of n. So I can look at their difference in terms of as a function in n. And then I can use my calculus. I can look at the derivative and see if the function is increasing or decreasing. So this is another way. And third way, since this is everything is based on the integers, third way is to look at the induction. So using any of these three, if you can show that this is monotonic increasing or decreasing, here I have already got for the increasing for the first part. So I'm basically looking whether it's monotonic increasing. Then you can say about the convergence, provided it is bounded above and on. So here, what do I know? So here actually basically you can try induction in the sense that when you look at xn plus 1, okay, so what I am looking at, I can look at xn plus 1 square minus xn square. So this is actually 2 times xn minus 1. So clear, it is clear that there is a relation of n plus 1 and n in terms of the previous terms, xn and xn minus 1. So if this is greater than 0, this is greater than 0. So hence by induction, I know that x2 is greater than x1. So if xn is greater than xn minus 1, I am getting xn plus 1 square is greater than xn square. And since x1 is all positive, I'm also taking the positive square roots when I'm looking at xn plus 1 and xn. So under that thing, I can see that, yes, my xn is monotonically increasing. And now monotonically increasing, and you also need to show that it is bounded above. So what actually you can show here is that 0 less than or equal to xn is less than or equal to 2. Now, if you want to show that this is less than or equal to 2, again you can apply using induction. Because x1 is root 2. It is less than or equal to 2. Now, x2 is square root of 2 times root 2. Now, here again, you can show that this is greater than 2. And hence, by induction, you are able to show that this xn is greater than or equal to 2. So, one more problem I can suggest from this direction in terms of this. This is slightly different from what we normally take in terms of the recurrence relation. This is 4 plus 3xn divided by 3 plus 2xn. So again, basically everything in analysis is about comparing how the terms are going to be. So I'm also doing let's see what happens if you directly look at the difference xn plus 1 minus xn. So this is actually 4 plus 3xn divided by 3 plus 2xn. This is 2 plus xn minus 4 plus 3 into xn minus 1 divided by 3 plus 2 into xn minus 1. So when you are doing this, you can show that it's actually equal to xn minus 1 divided by 3 plus 2 xn into 3 plus 2 xn minus 1. So if you want to show that this is greater than 0, you need to show that this is greater than 0. So again, induction process is coming. So this is the case where you are actually applying this and this together. So and then what about the denominator? So do you know the denominator is greater than 0? So you can also show that again by induction, each of these xn's are greater than 0. x1 is 1, so x2 is bigger than 1. So if xn is bigger than, x2 is big, we are looking if they are greater than 0. So again by induction, if you can show that xn's are bigger than 0, xn plus 1 is also bigger than 0. Hence you know that the sign is only depending upon the numerator. Denominator is not going to contribute to the sign because denominator is anyway positive. Hence, the sign is going to depend on the sign of this, and then that you can derive from induction. Hence, you are telling that, you're proving that this xn is actually monotonically increasing. And once you know that it is monotonically increasing, you need to give a upper bound. You need to tell that this is bounded above. So what could be a bound that you can use here is, again, for that you are writing xn plus 1. So xn plus 1 is actually 4 plus 3xn. And denominator is 3 plus 2xn. So I'm writing it in terms of 3 plus 2xn plus whatever is left out. This is 1 plus xn divided by again 3 plus 2xn. So this is actually 1 plus xn divided by 3 plus 2xn. Now again I'm comparing this. So 1 plus xn divided by 3 plus 2xn. You know that xn's are all positive. So this is 1 plus xn. So this is greater than 1. And this is also greater than 1. But this is 2xn. So 2xn plus 3 is there. Clear that the denominator is bigger than the numerator. So I can make this whole term less than 1. So this is less than or equal to 2. So I know that now see this monotonic increasing and bounded above. Hence it converges, and where it will converge? It will converge to the least upper bound. But that now actually you can use the fact that since you know that xn is converging, say if xn is converging to L, because of this relation I am having, I know that here what I am going to use? I'm going to use my properties of the sequence. If xn is converging to L, yn is converging to k, what happens to the sum of the sequence? What happens to the quotient of the sequence? So by that, I will get that on one side, this is L, and on the other side, this is 4 plus 3L divided by, this is 3 plus 2L. So now from here, I'll get a quadratic equation in terms of L. Now you are getting L square equal to 2 you will get. From here L equal to plus or minus 2. But you already know that all the things are positive. So L cannot be minus 2. Hence L has to be 2. Yes. Oh. So now another problem on the sequence. So with this, we'll stop sequence and then go to the series. So I'll go a little faster. So let 0 less than B1 less than A1 and define AN plus 1 equal to AN plus BN by 2 and BN plus 1 equal to square root of AN BN for all n in N. Now you are given a relation between AN and BN in terms of the n plus 1 terms, and you also know this. So what actually you can see from here, this and this. Whenever you are seeing an expression with sum of two terms divided by 2, and if the same expression is coming inside as a square root, the one inequality that comes to your mind is arithmetic mean and geometric mean. So arithmetic mean is always greater than or equal to geometric mean. So I am taking the arithmetic mean of two numbers, an and bn. So arithmetic mean of an and bn is given by an plus bn by 2. And geometric mean of an and bn is given by square root of a and bn. So I know that this happens. So from here, I'm automatically getting that n plus 1 is greater than or equal to bn plus 1. So this I know. Plus I know that a1 is lying between, so b1 is lying between 0 and a1. So from here, I can actually show that b1 is less than or equal to, yes. So this is, now I need to show about monotonic increasing or decreasing. No? So let me also now use this inequalities about an and bn. So bn plus 1 equal to square root of an bn. So this is less than or equal to. Since bn plus 1 is less than or equal to an plus 1, I know that this is less than or equal to an square, which is actually an. And on the other hand, I know that bn plus 1 is square root of an bn. So this is not going to help me. I already, yeah, maybe it may help me later, but not directly helping me to conclude about the monotonic increasing or decreasing of bn. So I should have replaced this an by bn itself. So if I replace this by, so this is square root of bn square. So this is bn. Okay. So this is what, how do you play with the inequalities? You try to put one thing which you know, but it didn't help you to conclude directly. So then you automatically came and looked at the other possibility that you need to find. So there is nothing magic happening here. We are trying our possibilities. If something didn't work, we come and look at the other possibility. So this is bn plus 1 is greater than or equal to bn. So that means the sequence bn is now increasing. And with this, I know that my b1 is less than or equal to, b2 is less than or equal to, etc. less than or equal to bn. But I now know that what is the relation between bn and an. Okay. And I also know that, so what I am, and b1 is less than or equal to, so what I am able to conclude from here is this, and b1 is less than or equal to bn, which is less than or equal to an. And what do I know about an plus 1? I don't know about an plus 1. So let me also write about an plus 1. So this is an plus bn by 2. So this is now less than 2 times an by 2. This is less than an. So now I know that sequence an is decreasing. Okay. Hence I know that is why I wrote here an less than or equal to a1. Okay. I should have been careful here. So this is ultimately I know. So I know about the bounded monotonic increasing and decreasing about bn and an. Also, I gave about the possible lower bound. So I know sure that it is bounded below, bounded above, and all. Hence, n and bn converges. Okay. So one more problem that uses arithmetic mean, geometric mean inequality. So this is 8, 9. So let a greater than 0 and x1 greater than 0. So you define xn plus 1 equal to half into xn plus a by xn for all n. show that xn is converging to root n. So again, so if you look at this expression, you can see that this is actually arithmetic mean of two numbers given by xn and a by xn. So if I want to talk about arithmetic mean, geometric mean inequality, so geometric mean of these two numbers will be square root of xn into a by xn, which is actually square root of a. So at once you are able to write that all this xn plus 1 are this is greater than or equal to square root of a. So you know a lower bound of xn plus 1 in terms of square root of a. Then you can directly show that xn plus 1 minus xn is actually positive, and hence this is so this you can show that this is negative. Hence you can show that xn is decreasing and it is bounded below. So this converges, and then by this limit property, you will get a relation for L, and you can ultimately, when you solve that equation, you will get that yes, L is actually square root of A. Okay. Okay. So one more thing I can talk about sequence in another 5 minutes. So this is about Cauchy sequence. I know that you know the definition of Cauchy sequence. The Cauchy sequence is telling that, so you are talking about xn and xm in terms of the distance between them. So what happens to xn minus xm when n and m are arbitrarily large? So can you make their difference as small as possible? Yes, you can make. So for any epsilon you want, there is a stage such that whenever you take m and n greater than or equal to n, the difference between terms, arbitrarily large terms I'm taking xn and xm. So even there, the terms arbitrarily large in the sense that I'm looking at the index. So whenever I look at n and m greater than or equal to n, their difference again I can make it to be less than epsilon. So you can show that if a sequence is Cauchy, so convergence and Cauchy. So if a sequence is Cauchy, if xn is Cauchy, will imply that xn converges. So one thing, if you have a sequence and if you want to check about the convergence, is that you can directly check whether it is Cauchy, and if it's Cauchy, you can tell that it's converging. Now, there is one more thing that we can mention about here. We are talking about the difference between n and m. So what if I am looking at the difference between consecutive terms of the sequence? What if I know that this happens, like for every epsilon greater than 0, there is a stage n such that for every n greater than n, this happens. So is it enough to conclude that the sequence is convergent from here as in terms of Cauchy? The difference between this and this is that this is already underlying in the Cauchy. Okay, but this is very weaker when you compare it with the Cauchy. This is only talking about the difference between consecutive terms of this sequence, whereas this is talking about difference between any term after a stage. So there definitely this is weaker, and this is not enough to conclude about the convergence. As you can see with the example xn equal to 1 by n. Sorry, this won't help. This won't help. Yeah, so you can take the sequence xn to be root n. So you have a sequence which is not converging, but the difference xn plus 1 minus xn. So this is square root of n plus 1 minus square root of n. So this is going to 0, this difference, but the sequence is not going to be converging. So, but there is an equivalence condition of Cauchy given using contraction principle. So let me write that and we can use it to do one or two problem here. So suppose 0 less than alpha less than 1 and xn is a sequence satisfying mod xn plus 2 minus xn plus 1 is less than or equal to alpha times mod xn plus 1 minus xn for all n, then the sequence xn is Cauchy. So let's compare the difference. So this is also talking about the difference of consecutive terms. But here I am comparing consecutive terms on the left-hand side and consecutive terms on the right-hand side with an additional contribution of a parameter alpha. where I know that alpha is strictly less than 1. So with this information, actually I am able to conclude that the sequence is Cauchy. So if you have this, from here you can conclude that xn minus xm is actually the difference between arbitrary large index terms are also going to be as small as possible. So why I am using this condition? So if you have sometimes maybe directly checking Cauchy may be difficult. So in that cases, you can come to this problem and see if there is a contraction. And from there you can tell that yes, it's Cauchy and hence it is converging. So I will not do the proof here. Actually, how does the proof comes? I can just tell you. So if you look at xn minus xm, you keep on adding all the intermediate terms. So this is xn. So let me take n is bigger than m. So this is xn minus xn plus 1 plus xn plus 1 minus xn plus 2 plus xn plus 2, etc. minus xm minus 1 plus xm minus 1 minus xm. And then you can see that when you take a triangle inequality, this and this again and again you can apply this given statement. So there are terms which involves alpha will come. So ultimately this will be like alpha raised to m minus 1 by 1 minus alpha into modulus of x2 minus x1. And now here everything is depending upon alpha. This actually tells why do we need alpha to be less than 1. See, if alpha is less than 1, then this limit will be going to 0. This is a fixed number. There is no n here. So this is a fixed number. So here everything is depending upon when you take m going to infinity. When you take m going to infinity, this fellow will go to 0. So I'm able to conclude about the sequence being Cauchy by this property. So let's do one problem based on this. So let x1 equal to 1 and xn plus 1 equal to 1 divided by 2 plus xn. The question is xn converging? Okay, one way to look is whether it is monotonic increasing or decreasing, but sometimes monotonic increasing or decreasing may be difficult to show. But if it happens, you're happy. But if otherwise, you can look at this xn plus 2 minus xn plus 1 here. So this is actually 1 divided by 2 plus xn plus 1 minus 1 divided by 2 plus xn. This is actually modulus of xn minus xn plus 1 divided by 2 plus xn plus 1 into 2 plus xn. Now, what do I want? I want to show that xn plus 2 minus xn plus 1, their difference is less than or equal to some number less than 1 times the difference between the other two terms. So other two terms have already come here. Now I only need to bring that alpha here. That clearly will come from this denominator. So how do I bring that alpha here? Now again I need to give an estimate for this product. 2 plus xn plus 1 and 2 plus xn. So what do I know about this xn's? At least I know that all of these xn's are greater than 0, right? Because x1 is 1. So xn plus 1 is 1 divided by 2 plus xn. So by induction, you can show that xn's are all greater than 0. Hence, these are all greater than 0. So definitely this is greater than 2 plus 0 into 2 plus 0, which is actually 4. So 1 divided by that will be less than 1 by 4. So from here, I am getting this fellow is less than 1 by 4 times mod xn minus xn plus 1. Hence, I am able to do that contraction theorem with alpha equal to 1 by 4. So you are telling that xn is actually Cauchy. And hence, it converges. Yeah. Okay. Okay, now, so now I'll go to series. So now how do you talk about series? So you have a sequence AN, and using the sequence, you're constructing a series. So say this is your series. So now you want to talk about the convergence of series. When do you tell that the series converges? So if you want to talk about the convergence of a series, you're going to construct another sequence from this ANs. So what is that sequence? I'm calling the first term of the sequence to be A1, second term of the sequence to be A1 plus A2, and so on, and so on. the nth term of the new sequence I'm constructing is given by a1 plus a2 plus etc. plus an. So I can look at the new sequence Sn and see whether this sequence is converging or diverging. So if this converges to say L, then I'm defining my series An. So the limit of this is actually nothing but the limit n tends to infinity of the sequence of the partial sums, which if it converges, it is converging to L. And this limit only I am defining to be the convergence. Where is the series converging to? The series converges, and the limit where it converges is given by the limit of the sequence of partial sum. So ultimately, finding the limit of a series is actually coming down to finding the limit of a sequence, which now you know, or anyway you know by using all the different properties of the sequence. So in addition to that, again, you have already seen there are many tests. So say I'm looking at ANs are all greater than or equal to 0. Okay. Then say this is the particular case I'm looking. Then there are so many things I can talk about my sequence, my series. So if the series is convergence, so if summation AN converges, that means the sequence of partial sums converges. That means my AN is actually Sn plus 1 minus Sn. So Sn plus 1 is converging to L and Sn is also converging to L. So this AN will converge to this L minus L, which is 0. So this is one thing that I can directly derive. If you know that summation AN converges, then AN should converge to 0. So this is called nth term test. What about the converse? If you have that AN converging to 0, can you say that summation AN converges? Need not be. An example is AN equal to 1 by N. So this is converging to 0, but you know that summation 1 by N is divergent. And why summation 1 by N is divergent? Again, when you look at the sequence of the partial sums, you know that the sequence of the partial sums should converge. And you know that the convergent sequence is bounded, right? But you can show that the sequence of partial sums given by the summation 1 by N is not bounded. Hence, it is not converging. Okay? So all the theorems that you have done with the sequence is actually helping you to talk about the convergence or divergence of the series. And in addition, you have comparison test. So comparison test. And then you have limit comparison test. And then you have very helpful root test, ratio test. So these are also applicable when ANs are positive and negative. And for alternating series, you have Leibniz test. So those tests where you can readily apply, for example, root test, ratio test, and all, you only need to find what happens to the limit of the ratio or limit of the AN raised to 1 by N. And once you know the limit, you know what it happens. But how do you derive this root test and ratio test? It ultimately goes back to the comparison test and even the integral test. So integral test is basically comparing a sequence, a series in terms of an integral, because the area coming from this integral function is actually giving you that rectangular blocks where the series, where the sequence of partial sums is coming. And so if you look at how all this root test, ratio test, this integral test works, it actually comes back to this comparison test. So if you know how to compare between terms, which anyway we were doing in the terms of the sequence problems also. So ultimately, many things is boiling down to how you are comparing two expressions in terms of n. So I'll do some problems based on this comparison test. So first one, okay. So again, let n greater than or equal to 0. If summation an converges, then can you say anything about summation n square, whether it converges or diverges? And what about the converse? So converse, it's not true, right? This we can say. Converse means I know that summation n square converges, but summation an is not converging. Example is summation 1 by n square converges, but summation 1 by n does not. So let's look at this. I know about an, summation an. Can I use this to talk about summation an square? So what actually I'm going to use is this nth term test. If summation an converges, then I know that an is converging to 0. So since summation an converges, I know that an is converging to 0. Now what do you mean by an is converging to 0? That means I'm able to make the difference between an and the 0, which is mod an, as small as possible. So okay, as small as possible. So for any epsilon, I'm able to do it. So let me choose epsilon equal to say half. Okay. So I'm able to make mod an is less than half for all n greater than or equal to some integer n. So there is an n in the natural number such that this happens. That is what meant by n is converging to 0. Now I want to talk about n square. So if I look at n square is less than or equal to n into, so mod n square if I write. Anyway, this is mod positive. This is n and mod n. Now, I have also given that ans are greater than or equal to 0. So I don't need to worry about mod an. This is same as an. Okay. So I can avoid this modulus here. So this is less than or equal to an into an, which is less than or equal to half. So now I'm comparing this with half an. So comparison test tells that if you know an less than or equal to bn, and if you know summation bn, if you know that bn is a series which converges, then summation an. So this converges if summation bn converges. Okay. So now this, and also another thing what you are using is, if you know summation an converges, then a new series that you are constructing by multiplying each an by a constant summation can, and this will also converge. So I know that summation half an converges, and this is my bn I am taking because an converges. Hence, by comparison test, we know that summation n square converges. Okay. So now what about, suppose I am giving the same thing, n greater than 0 and summation n converges. And can you talk about summation square root of n into n plus 1? Is this converges or diverges? So again, this is square root of n into n plus 1. We did geometric mean, right? So I can also compare geometric mean with arithmetic mean. So if I look at the arithmetic mean of n and n plus 1 by 2, so this is less than or equal to square root of n and n plus 1. So I directly got what I am comparing it with. So I am comparing the nth term of the series with n plus 1 by 2. So this is nothing but n by 2 plus n plus 1 by 2. Now n converges. So this is a nth term of a series which is converging. Now since n converges, n plus 1 by 2 is also converge when it comes as a nth term of a series. Hence, this if I call it bn, I know that summation bn converges, which will imply this fellow will also converge. Again, comparison test. So basically, everything in this series is ultimately coming to comparison, either it is limit comparison or direct comparison. So another one. So again, under the assumption that summation n converges, what can you say about summation n plus 4 raised to n by n plus 5 raised to n? Whether this will converge or not. Again, comparison. I need to compare. So I am bringing n plus 4 raised to n by n plus 5 raised to n. So here I know that ans are greater than or equal to 0. It is given to me. So I can, whenever you are comparing, you are trying to eliminate the denominator in terms of either a some function which is easier to compare. So I'm looking at n plus 5 raised to n. This is greater than or equal to 5 raised to n. So 1 by n plus 5 raised to n is less than or equal to this. So we are getting this is less than or equal to n plus 4 raised to n divided by 5 raised to n. So which is actually n by 5 raised to n plus 4 by 5 raised to n. Now, n, you know, this converges. So it's only about now this 5 raised to n. Now 5 raised to n if you look at 1 by 5 raised to n, and if you look at this summation, there's a geometric series whose common ratio is less than 1. So this fellow converges. Hence, this summation an bn, if you know about an and bn converges, and summation an bn converges. And this is again a geometric series with common ratio less than 1. So this converges, and some of the two series will converge. Hence, this fellow will also converge. Okay. So same way, you can go back and see, suppose now I have another sequence. Let n be a sequence such that n is greater than 0. Now instead of n converging, I'm given that n is tending to infinity. Okay? Now what about summation 1 by n raised to n? Okay? So here what you can observe is that n is going to infinity. So that means given any real number m in R, I am able to tell that mod n is greater than m for all n greater than or equal to some stage. That means 1 by mod n. And again, n is greater than 0. So this is n. So from here, I am getting 1 by n is less than or equal to 1 by m. Okay. So I am now able to compare 1 by n raised to n to be less than or equal to, this is 1 by m this raised to n. And now you can talk about this. Now m, I can actually, this is for any real number, given any real number. So I can now choose my m such that 1 by m is less than 1. So you can choose your m to be 10 or 100 or anything. And then this will be less than 1 by 100 raised to n. Okay. So from the definition, how are we doing these problems? Okay. Now let's look at some series which involving logarithms. So before doing the logarithms, many times whenever we have to compare a function where in the numerator and denominator logarithm comes, what actually we need to understand that we are comparing the function. So say if I am comparing the function x and ln of x, okay, which one is bigger or how much bigger? So this is clear that x is bigger than ln of x, right? But even much more is bigger. Like I can actually tell that it's not only x, ln of x is actually less than x raised to any power that you choose here. So any power means any positive power that you choose here. So if I look at x raised to half, similarly, ln of x is less than x raised to any power, 1 by 100. So this is going to be true for every x. So this you can compare the functions of x and ln of x. Why it is true? Because if this is ln is in terms of natural logarithm in terms of e. So instead, if you would have taking the logarithm with respect to base 10, you can see that when x is actually of the form 10, 10 square, 10 cube, 10 raised to 4, if I look at logarithm of x with base 10, this is actually 1, 2, 3, 4. So you can see how logarithm, how much this is growing, but this logarithm is a very slow growing function. Even though logarithm of x is also going to infinity as x tends to infinity, when you compare with the function x, the rate of logarithm is very, very small as compared to x, in the sense that you can compare now logarithm of x with even other smaller powers of x. It could be x raised to r, where r is greater than 0, okay, with any power. So what does that mean? That means if I'm looking at ln of x and x raised to half, so it may not be true that ln of x is less than x raised to half for every x, but instead I will get that this is true for every x greater than or equal to a stage, some x naught. Similarly, ln of x is less than x raised to 1 by 100 for every x greater than or equal to some other stage, let it call x1. So now, how do you, if you want to prove this, how do you do? You can look at your calculus. You can consider your function f of x equal to x raised to 1 by 100 minus ln of x and look at the derivative. And if you can show that the derivative is greater than 0 for all x greater than or equal to some stage, that means your function f is increasing from that stage onwards. So the key thing is that instead of this 1 by 2, 1 by 100, I can put it to be any number r. So this is how you are comparing x with ln of x. Now on the other hand, I can also compare. Yeah. So this is the main comparison that we need to. If you keep this in mind, anything involving with ln of x will be able to follow easily. Okay, so let's look at this. So I'm looking at summation an. So I want to talk about the given an. Check if summation an converges or diverges. The first one, so you are giving an equal to ln of n divided by square root of n. Yeah. Now the square root of n is there and ln of n is there. And you know that if you look at n and bn, and if you can talk about limit n tends to infinity, I'm looking at, earlier I was looking at direct comparison test. I did not use any limit, or I could have used the limit here. Here and all, I did not use any limit. I was comparing them directly. This, yeah, actually I should have talked about the limit there also, because I'm telling n is less than half for all n greater than or equal to n. So there was a limit thing coming there. It was not direct comparison. Okay, but here I'm actually taking the limits directly. So this is called limit comparison test. So limit n tends to infinity, n by bn. So what happens to this limit? If this limit is this limit infinity, or is this limit 0, or is this limit a positive number, c, which is greater than 0? Depending on that, you know that. And if you have information about bn, can you talk about the convergence or divergence of an? So these are called limit comparison test. So here, now the only thing that you need to be careful here is how you are choosing your bn. You need to choose your bn such that applying the limit comparison test, you will be able to get your answers directly. Otherwise, you may be choosing a bn, the limit may be giving here, but the conclusion may be depending on whether the bn is converging or not, but you may have chosen a diverging thing. Okay, so that is the only thing that you need to be careful. So let me take bn equal to 1 by root n here. So if you take bn equal to 1 by root n, then n by bn. So this is ln of n by root n, 1 by root n. So this is root n. So this is ln of n. So this will go to infinity as n tends to infinity. And what do I know about summation bn? So this is summation 1 by n raised to half. So this diverges. So what I have used there is about summation 1 by n raised to p. So this diverges if p less than or equal to 1, and summation 1 by n raised to p converges if p greater than 1. And how you can show this? This is again from comparison, or you are actually using integral test, which is again for like from comparison test. So from integral test, using integral test, once you show this, then you are able to use this directly whenever you need it. So you know that this diverges and n by bn is going to infinity. So when you have this going to infinity, and if you know bn diverges, then you know that summation an also diverges. Okay. Then second one, again in terms of this n in terms of ln, so it is 1 by ln of n raised to p, where I am taking p greater than 0. See, whenever you are having a parameter without involving n, you need to mention what is the range of p that you are choosing, because according to the different possibilities of p, you may need to consider different cases. Okay. So here I am looking at bn equal to 1 by n, then n by bn, what will it happen? So why I am looking at, if whenever log n comes, I'll be mostly looking at bn in terms of n raised to, it will be bn in terms of n raised to some positive power, or it will be 1 by n raised to some positive power. So either one of this I'll be choosing. Okay. Now, sometimes I may need to work out the inequalities at the back end to choose whether you need n raised to a positive power or 1 by n raised to positive power. Okay. But thinking of that is actually coming from this. Now, n by bn, when you are doing this, this is actually 1 by, so n by bn has come, so n is going up. So this is ln of n raised to p. Yeah. So when I was doing the comparison here, I was comparing ln of x with a power of x, with a positive power of x. Now I am comparing here f of x equal to x with g of x equal to ln of x raised to a positive power. So here power has now come into the ln of x. Normally, you know that when there is a power, okay, depending on whether the power is greater than 1 or not. So for example, if I am comparing ln of x square with x, I know to compare ln of x with x. But what if I am comparing ln of x square with x? Is still x very large compared to ln of x square? Yes. Why? Because again, ln of x square. So if you have a doubt whether which one is bigger or smaller, what you can actually know that this is less than x. If and only if I can take one more logarithm, 2 times ln of x is less than ln of x. And now I am comparing, this is my x instead of ln of x is sitting here. So earlier I compared how x and ln of x is functioning. So in the same way now I am able to compare 2 times ln of x with x. Okay, so this is also true. So we have actually showed that. Yeah. So what actually here we are actually looking here is ln of x raised to any p. So instead of 2, it could be any p where p is positive. So how you are comparing? You are now comparing x with a constant times ln of x. This is actually a constant time, whether it is 1000 or whether it is 10,000 or whether it is 10 raised to 100 times ln of x. Even then, you are able to show that x is bigger than this after a stage. Okay, after a stage will come because for the initial first some finite like in a bounded set of real numbers, this may not be true, but after that this may not be. This may be true. Okay, so this is what I am comparing here. I am comparing the function x with ln of x raised to p. So which one is bigger? Naturally, ln of x raised to p is smaller than x. And how smaller it is? So it's actually very small in the sense that I can show that ln of x raised to p is actually smaller than x raised to half. Okay. So if I show this, then what I am actually getting is n by bn equal to n by ln of n the whole raised to p. So if I show that this is less than this, then I'm getting, okay, sorry, now here I need to make a rearrangement here. So half may not work because half has a problem. Now I cannot, that summation n raised to, I need to look at something bigger. So what I may have to see here, so even though this is true, this may not be helpful for me here. Actually, what I want to show here, this is n by n of p. So if I can show that this is, yeah. So I want to talk about 1 by ln of p, right? So I should have told about, yeah. What if I, so this is not going to be helpful directly here. What if I compare ln of x with, so I want to show that this is actually less than, say, n raised to, this is there, this is 1 is there, n raised to 1 minus some number. Okay. So it could be, it could be like 1 minus 3 by 4 also. It could be 1 minus, yeah, 3 by 4 is fine. So if I show that this is less than 1 raised to 1 minus 3 by 4, this is actually n raised to 1 by 4, which will go to infinity as n tends to infinity. So to show that n by, okay, so let me also take n also. It may not be only possible with ln of x. So I need to now take ln of n raised to p is less than n raised to 1 minus 3 by 4 means I actually want to show that this happens, n raised to 1 minus. This happens if n raised to 3 by 4 is less than ln of n raised to p. Oh, so that won't work. that won't work. This happens if 3 by 4 ln of n is less than p times ln of n. And this happens if 3 by 4 is less than p. Okay, so I need my p to be greater than 3 by 4 to do that. But p is actually any number greater than 0. Okay, so I need to now modify here. Yeah, so here I need to now give an expression in terms of p. So it's not that n raised to 3 by 4 that I can work with. I cannot fix a exponent here. I also need to write it in terms of something in terms of p. Okay, so that p will come here, and then I can tell that yes. So I know that p is greater than 0. So I should have get here p greater than p by 2 form. So instead of 3 by 4, but p is less than 1. No, p is greater than 0. Oh yeah. So here you may need to now consider some cases. Because if I'm looking at p less than 0, now there are possibilities depending on 0 less than p less than 1 and p greater than 1. Okay. So this is one thing that, so yeah, one we need to be careful about here this. Because this p is actually coming in our exponent of n that we are choosing here. Okay, what should be the p that I need to choose? And ultimately, that is only coming from how you are comparing p and p by 2. So you know that if p is greater than 1, this is true. But if p is less than 1, p is less than 1, what do you know about p and p by 2? Yeah, then also you know that p is greater than p by 2, right? Okay, yeah, this is true. Yeah, so we don't have any problem. So instead of 3 by 4, we only need to make it p by 2. So that means here instead of 3, this should be p by 2. Hence, I'll get this should be n raised to p by 2. So then this will be p by 2 times ln. Yeah. So yes. So this I'll get. Since this is true, this will follow. Hence, I'm able to make this fellow less than n raised to 1 minus p by 2. But again, you see, if you want to tell that this is going to infinity, it's clearly depending upon how much saving you have here. So you need your 1 minus p by 2 to be greater than 0 to tell that this is going to infinity. Otherwise, this is going to 0 depending on if p by 2 is greater than 1 or not. Okay. So clearly, this distinction about p should also, we should consider the different cases. I hope this is fine. Okay. So this is the game that we need to do whenever LNX come. We really need to see what power that you need to choose so that things can get adjusted. Okay, so one more term with ln of x. So this is an to be 1 divided by n square minus ln of n. So now here comparison is slightly easier because I'm comparing now ln of n with n only. So because of this, I know that this is less than or equal to 1 divided by n square minus n. So this is 1 divided by n into n minus 1. So either, since you are looking at the limit comparison test, you can think of this as approximately equal to 1 by n square, or you can, even if you want to be particularly writing, you can show that this is less than or equal to 1 by n minus 1 square. And since you know about summation 1 by n square being convergent, you can talk about summation an also to be convergent. So another thing, yeah. So another sequence, n plus series. Sorry, this is ans, and we are looking at what happens to summation n. So sequence is given by n plus 2 into 1 minus cos 1 by n. Okay. So this is your an. The question is summation n convergent? So I have to look for some comparison. So this is with n plus 2, but nevertheless is greater than or equal to n times 1 minus cos 1 by n. Okay. So if I know about a series that has terms like summation n into 1 minus cos 1 by n, okay, then I can talk about, so and say if I know it is diverging, then I can tell that summation n is diverging. So let's see whether this is diverging or not. Diverges or not. So if say this would not have been diverging, then I should have looked at an upper bound and say that whatever that upper bound, if that series is converging, then this will converge. So this is how we keep on changing whether to look at divergence or convergence. Okay, also another term, whenever you have a question to look about the series divergence or convergence, you can always see whether the nth term test fails or not. If n is not going to 0, at once you can tell that summation an is not convergent and hence divergent. Okay. So now I need to talk about whether this diverges or not. So again, I need to look for the comparison. So I'm comparing it with bn equal to 1 by n. This 1 by n is here and n is here. So if I look at, so if I call my Cn to be, this is my summation Cn, and Cn to be n into 1 minus cos 1 by n, then Cn by Bn, this is actually 1 minus cos 1 by n, so divide by, so 1 by n is there, so Cn is also there, so n is here, so 1 by, no, this was n, so I'm dividing, so it will be n square. So this I can now write it as 1 minus cos 1 by n divided by 1 by n square. Okay, and you need to find what is this limit. So this limit, you can find it to be half. Okay, so this is a limit which is not equal to 0. And so what happens is that if this series, yeah, I'm comparing it with 1 by n now. So that I know summation 1 by n diverges. The summation 1 by n diverges. Therefore, summation n into 1 minus cos 1 by n, and hence summation n plus 2 into 1 minus cos 1 by n also diverges. Okay. So again, we did the comparison test. Now, one more problem we can do in this direction. So here an equal to 2 plus sine cube n plus 1 divided by 2 raised to n plus n square. Okay? And now you need to talk about what happens to summation an converges or diverges. Okay, so an is like this. We also know that if an and bn converges, then summation an plus summation bn. If you know about an and bn converging, then you can talk about summation n plus bn in terms of this. So that's what we are going to do here. So I'm trying to split it as 2 divided by 2 raised to n plus n square plus sine cube of n plus 1 divided by 2 raised to n plus n square. Okay. So if I can think of this as nth term of a series and this as nth term of another series, and if I can talk about the convergence of them separately, I can talk about the convergence of an. So let's look at 2 by 2 raised to n plus n square. So this is 1 by 2 raised to n and 1 by n square I'm comparing. Okay. So 1 by 2 raised to n is less than 1 by n square. Why? Yeah. Again, see, I'm actually comparing 2 raised to n with n square. Which one is bigger? So if you put some initial values of n, you can see that 2 raised to n square is slightly bigger. But after n equal to 5, you can see that 2 raised to n is bigger. If you want to show that this is bigger, what is the easy way? Take logarithm. So this is n times log 2 should be bigger than 2 times log n. And so this is if and only if. And this happens if n by 2 is bigger than log n by log 2. Log 2 is some number. This is some number. So essentially you are comparing n with log n, okay, which you know that n is actually bigger than log n. So you know that this follows. Hence you know that this is actually less than, so 1 by 2 raised to n plus n square. This is less than 1 by 2n square. So 2 by this will be less than 1 by n square. And this, you know, converging. Hence, summation of this will converge. Now only sine cube of n plus 1 is remaining. So there you can take the absolute value. So you know about absolute convergence. Absolute convergence, you know. So this tells that if a series converges absolutely, then the series convergence absolutely means instead of an, you are looking at summation mod an. So if it converges absolutely, then it will converge. So I can look at sine cube of n plus 1 divided by 2 raised to n plus n square. Okay. So this is less than or equal to 1 by 2 raised to n plus n square, which I have again applying in this way. You can show that this is converging. Okay. Hence again by comparison test, this will converge. So one more common problem that is very common is square root of n plus 1 minus square root of n by n. So if this is an, what will happen to summation an? So this kind of things, you know, that conjugate multiplication that you can do, which is root of n plus 1 minus root n times root of n plus 1 plus root n divided by n into root of n plus 1 plus root n. So this is n plus 1 minus n divided by n times square root of n plus 1 plus root n. So you are actually comparing 1 by n times square root of n plus 1 plus 1 by n times square root of n. And you know that 1 by n times square root of n, this converges. Okay, hence this and this will converge. So maybe I can stop the problem session here.
My name is Subhra Kundu. I am come from West Bengal.
Yes.
So thank you, ma'am, for the very much nice session. And problem is very collective problem.
Okay. Have you seen these problems earlier, or like
few maximum problem is new. So it is.
Okay. Yeah. Oh, I'm happy to hear that. That was
Yes,
one thing I was worried. Like, since I don't know what was happening in the earlier sessions, or you may be looking at problems by yourself.
Explanation is very easy and authentic by Sandwich theorem. Is so.
Yes. So I just want to tell you one thing. Like, now you know Sandwich theorem, you know how to apply. But of course, go back and look at the proof.
Yes.
And see what are the conditions that you have given. How you have used the conditions. Like, given any theorem and proof, you should always look and see whether the conditions given in the theorem, have you used it correctly inside the statement, or whether that was needed, or something more you can add, or something you can relax. So once you kind of look into with this approach, then you will see that there is no magic happening. Like, otherwise, if you only concentrate on doing problems, and sometimes it will be little worrisome in the sense that you really don't know why we are taking this, why this is needed. Okay, so, but there is always a reason why we are choosing something. So look behind the reason, and then it will be more like understandable, and it will remain with you.
Yes, ma'am. Yes, ma'am. Thank you, ma'am. Ma'am, please give any suggestion for any reference book, real analysis. Any reference.
So if you're looking for the problems, then I know that you may be already knowing the books that contains more problems and all, right?
Yes, ma'am. Yes, ma'am. Only problems.
So okay, so there is one engineering textbook that we follow, which has lots of problems in sequence and series, which is given by Thomas Calculus. And then, of course, this, what about MAPA?
Yes, MAPA I have.
Yeah, MAPA has a very good collection of problems. And then S.C. Malik and Aurora. Then, and if you want to look into a little more theoretical way, then I'll suggest to look at Bartle, Shepard and Rudin, Principles of Mathematical Analysis by Rudin.
Okay, ma'am.
So that will take you to little more theoretical oriented problems, Rudin.
Okay, ma'am. Thank you, ma'am.
Yeah.
Thank you, Vinod sir, for your conducting very nice session.
Okay, thank you. Like, but you can give me the like.
We are very gratitude.
Don't need to.
Yes, ma'am.
You can tell me your like if you have any difficulty or something you missed, you can also ask about that.
No, ma'am. All are fine.
Okay, fine.
Very
Thank you.
Yes,
Thank
sir.
you.
Thank you, sir, for your dedication for me, for us. Thank you.
Yeah, this. Yes.
Yes, good afternoon, sir. Good afternoon, ma'am. The session was very nice and problem also very nice, and sandwich problem and logarithmic test and ratio test and limit ratio test, limit comparison test also. I can ask your PhD experience also.
Oh, yeah. So basically I'm trying to tell you that when you go, first of all, when you are going for higher studies, up to now, you may be in your own state, right? You may be doing your bachelor's in your own place, your own convenience, like local language is there, your friends are there, you are in a comfortable atmosphere. The moment you go out of the state, of course, some difficulties will be there in terms of food and living conditions, but you will be happy if your mathematics has been taken care, if your subject has been taken care. And how it will be taken care? Only if you are ready to communicate. So if in a class there is some discussion going on, you should be always willing to like ask your queries, stop the or ask the correct person, or ask the teacher, or ask the like your friends what is happening. You should not hesitate. Many times what happens is that because of the way our culture, we may be asked to keep quiet many times. Like it may not be very welcoming every time to ask questions, whether in family or whether in every, like in school also. So it can affect our way of asking questions. And we may be very much thinking that, oh, what if I'm asking a wrong question? It's okay. Even if you ask the wrong question, the other person is not going to think about it later. Like, so don't be worried about asking wrong questions. It's okay to ask wrong questions. So, but ask questions.
I'm Harita from Kerala. I'm a final graduate student preparing for my exams. The class was very nice. To be honest, as for me, it was a little fast, but the beginning was very slow. Then gradually it started becoming fast, but it was understandable. Some places I was getting stuck, but it was really nice session. Very great collection of questions, and we didn't know that everything was starting from the very simple comparison test, and you were using the same test for every questions, and that's the very point where we are getting stuck. Why are we choosing this BN, and from where is this BN coming from? That's the exact thing where we always get stuck, and you were working on that, and it was very convenient for us. And thank you so much. Thank you so much for your efforts as usual. Thank you, Vinod sir. It was very useful session. Thank you.
So next time, Harida, when you see if somebody is going fast, you can always tell that person. You can tell in between and tell that, can you please be slow here? That would. I was going a little fast in between because I was not sure whether these problems are already known to you or how it is. So just to cover some more things, I was going fast. Otherwise, I would have been happy to be even slower. Like, okay, so next time you can always tell.
Okay. Thank you.
Okay, thank you, Harita. Yes, others?
Hello, ma'am.
Yes.
I'm Iritty from NIT Trichy, and I am a MSc second year student. Ma'am, today's session was very helpful for our upcoming exam, and you discussed a lot of problems that help us really to prepare these exams. So thank you so much, ma'am, for your efforts and for your precious time for us. Thank you so much, ma'am.
Okay, but you are an MSc student, so what thing did you gain new from this session today? Or it was more or less?
Ma'am, actually, for exam point of view, the session is very good because in coming 10 days we have GATE exam. So it was the problem solving session was really good for us. That point of view for for revising the concepts or the how we can attempt the given problem. For that point of view, it was very helpful for us, for me also, ma'am.
Okay. Yeah. Thank you.
Yes, ma'am. Thank you, ma'am.
Okay, thank you, Titi. Others?
Hello, ma'am.
Am I audible? Hello.
Yeah. Yes,
Ma'am. Good
Nishita.
morning, sir. I'm Nishita Pendharkar from Maharashtra. I'm third year BSc student, and ma'am, today's session was very helpful for us, and the way you are taking all the problems and solving it was very interesting. I'm very thankful for you, and also I'm very thankful to Vinod Kumar sir, and thank you so much.
Yeah. So you could see why we are doing this way, or it was fast for you?
No, it was little bit faster, but I was getting like.
So were the problems new to you, or you have already done these problems?
Some problems was new to me.
Okay.
Thank you.
Yeah. Thank you, Nishita. Others?
Yes.
I am Tejaswini from Karnataka. I am studying in Rani Chennamma University, final year. Ma'am, I have one question about supremum and infimum. Means what the supremum and infimum of an empty set?
Okay, so whenever this empty set happens, see, whenever you want to talk about supremum is something as upper bound or lower bound, right?
Yes,
so if you don't have elements to talk about what are the bounds, like, so what happens when these are the like they tell that vacuum cases.
Yes, ma'am.
Okay, so I don't really know how do we define. So many of the times whenever this kind of vacuum cases come, we try to define something so that this question won't come again.
Yeah, Saranya,
yeah, ma'am. But we said empty set is bonded.
Yeah, let me tell something.
Yeah, maybe Vinod sir is yes.
Yes, sir.
See, in this case, in case of empty set, as there is nothing in that, every real number will be an upper bound for that. So
yes, sir.
There is a convention to take minus infinity as the supremum in that case. Okay.
Yes.
Similarly, any number will be a lower bound. So infinity will be a greatest lower bound, like that. Okay. So it's a convention to take like that.
Yeah.
Okay, sir. Thank you, sir. Thank you, ma'am. Ma'am, it was a wonderful session. The exam problems are new to me, and some of problems, and explanation was very good. And sandwich explanation is very good, ma'am. Thank you, ma'am.
Thank you.
Thank you, sir, for conducting such a session for us.
Thank you, Tejaswini.
Thank you, sir.
Ma'am, I am Anamika. I'm from Kerala, Kozhikode. Thank you, ma'am, for the session, and the problems discussed almost was new problems, and the way you used many of the questions you used limit comparison test, and it was so good, and it was easy to understand, and it will be good, ma'am, if you can share that your note today itself. I leave to note some of the problems, so it will be good, ma'am. And
Sure,
thank you, ma'am, for this session. And thank you, note, sir.
Thank you, Anamika. Yeah, others?
Hi, sir.
Yeah,
Sir?
Arya. Yes, Arya.
Hi, sir. My name is Arya. I'm a third year BSc Maths student from Kerala. And thank you, ma'am, for this nice section. And you explained the variety of questions, and it's really helpful for the exam preparation. And thank you, ma'am. And thank you, Vinod, sir, for this nice section.
Okay, thank
so
you,
I would
Arya.
also, yes, Saurabh.
Yes, sir.
Hi, sir. Hi, ma'am.
Yes.
I am Saurabh Kundu. I am from West Bengal, and now I am in BSc final year. The session was very good, and I got to know about various new aspects of solving sequence and series related problems. It was very nice. Thank you.
Thank you.
Thank you,
So
Sagar.
I would just like to point one more thing here. When you try to solve the questions given in the JAM previous exam papers and all, so there also, don't just look at the solution and try what is there. You pause a moment and see why we are choosing something like this in this step, why it is needed, or something else can I choose. With this, only you will be able to apply it again and again. So that was my intention also to put these problems and like. So I hope that would have reached, sir. Like maybe you can give a opinion about that.
Yeah. While a question setter arranging some question or preparing some question, there will be some intention to use some theory behind that. So he's preparing in such a way. So once you know the theory well, and if you know how to apply it properly, then that will be really nice, I think. Without simply learning the tricks and other things,
right,
there will be some intention behind that question. So while setting a question by a question paper setter, certainly he is looking at some theory and how to make it a problem like that. Such a thought may be there behind any good questions, I think.
Yes. Yeah, making a good question is actually looking back into the theory and see if in the theory there is a condition, then remove that condition and put something else, and whether that is how problems are being made.
Is others?
Hello, ma'am.
Yes.
Yeah, Gayatri.
I am Gayatri. I have done my graduation from Miranda House College, Delhi. The class was really nice, ma'am, and you have revised the theory part with the questions, and that was really needed for us in this last week preparation. And it was really good and useful. And each and every point that you were saying were really clear for me, and that's the best part. And thank you so much, ma'am, for taking such a wonderful class for us. Thank you.
Okay, nice to hear. Thank you.
Gayatri. Yes, others?
Hello.
Yeah.
Good afternoon, ma'am. Good afternoon, sir. I'm Shikha, second year MSc student from Birla Institute of Technology, Jharkhand. Ma'am, your session was really wonderful, and practicing such amount of question at this moment of time will really help us a lot in our upcoming exams. Ma'am, I would like to know what are tips we should follow for time management during exams.
Okay, time management. That is something which I'm really not good at with the exams, because see, the way we do in normal class and all, we try something and then we understand it's not working, then we come back and do it. But for exam, definitely you cannot spend that much time. So only thing to do time management in exam is to do more and more problems before exam, so that your familiarity will help you. When you look at a problem,
So, ma'am's voice is not there.
Yeah, Saranya. Hello, Saranya. You are not audible now. Maybe some network issues. Let's wait for a minute. Hello, Saranya. Are you there? Yeah.
Okay. So that will come by the more and more practice. And that will come when you practice, you ask also questions. If you don't ask questions while doing it at home, it will be difficult to keep in memory, like why we are using something like this.
Okay.
Okay, ma'am. Thank you, ma'am. Thank you, sir, for organizing such sessions.
Thank you, Shikha. Yeah. Any others? Yes. Yeah.
Hello, ma'am. My name is Abarna. I'm a graduate student from Kerala. Ma'am, today's session was very nice. Actually, I always had a problem with real analysis, and the concept questions, for me it's really hard. Like it takes time for me to understand all these concepts. So some of the questions where I already knew about it, and most of the questions I didn't know about how to solve it, or I always had a problem. And the most part is that I always had a problem with arithmetic and geometric, how to use it in all these questions. And from today's sessions I came to know how to use it. So thank you so much, ma'am, for for giving us this wonderful session, and also to Vinod sir for organizing this session. Thank you so much, ma'am.
Nice to meet you. Thank you, Aparna. Now, Gopika.
Hi, ma'am. I'm Gopika. I'm a Guriatpan College, Kerala. Today's session is really nice. As our JAM exam, it's a really important session for me, and it's really helpful for our preparation. Thank you so much, ma'am. And each of you really well. And thank you so much, ma'am, for your time and effort. Thank you so much, Vinod sir, for conducting this session. Thank you.
Okay, thank you, Gopika. Yes. Yes, Varada, you started to say something.
Good afternoon, ma'am. My name is Varada, and I'm from Kerala. Today's class was very amazing, and I honestly look forward to receive more classes from you. Thank you, ma'am.
Yeah. Thank you, Varada.
Thank you, Varada. Any others?
Hello, ma'am. Good afternoon, ma'am.
Yeah, yes.
Sir.
Yes, Shilpa.
Okay, sir. Good afternoon, ma'am. Today's class was very nice. You discussed many problems. Many of them were new to me, and the way of approaching the problem was also, you made it very easy by approaching it in a simple way and discuss, and also explaining it step by step. Thank you, ma'am. And thank you, sir. You always help us, and also by organizing such a online session in the last minute of our examination, you are helping us very much. Thank you, sir, and thank you, ma'am.
Thank you, Shilpa. Yes, Malavika.
Hello, ma'am. I'm Malavika, third year BSc Math student from Tirur College, Kerala. Thank you, ma'am, for this wonderful session. Most of the questions were actually new to me, and I clearly understood the questions you were discussed today. Thank you so much, ma'am, for your time and effort. Also, I would like to thank Vinod sir for conducting such a wonderful session for us. Thank you.
Yeah, thank you, Malavika. Any others? Yeah, Fatima Fida. Yes.
Today is my first class in Max Aspirants. I never joined any class before. So I think this is a problem. The heading is problem session. So I am a bit confused because I don't know the concepts, anything. I only know the third semester has some sequence and series in Calcutta University. So I think what I'm going to do, but ma'am explain some definitions before you going for a problem. So it's clear. So for me, the sequence part is very much clear. I get every problems. But at the last of series, I not get some concepts because I'm not familiar with that. But anyway, thank you everyone.
Yeah, Fatima, it may be because, as you are a third sem student, you didn't learn this before. That's why. Anyway, you have to learn this in the coming semester, so it will be really useful at that time.
Okay.
Okay, any others? Anu, are you there?
Yes, sir. Thank you, Saranya ma'am, for organizing this for conducting this class. It has been very helpful for the last minute preparation. And as our JAM exam is within 2 weeks, it has been like a revision of the concept, and it has been very useful to us. And most of the questions were new to me, and I understood it very clearly. And the concept of the sequence and series is almost thorough to me now. And thank you, ma'am, for spending your valuable time with us. Thank you.
Thank you, Anu. Any others? Okay, if any of you would like to
Dharmendra is asking something about, I can just see his message. Yes, actually, this is a Samsung tablet and I am writing in the Samsung notes.
Okay. Okay, any others?
Thank you, ma'am.
Yeah, thank you, Dharmendra. So I think we can wind up the comments. I think it's over, I think. So once again, thank you, Saranya ma'am, for being with us. And you have taken a lot of effort to prepare all these problems and all that. But your selection of the problems were really good because, they clearly give some new ideas to the students, how to use the certain theory in applying, so in solving certain problems. I think that part will be a really nice of today's session. So I'm very happy that you have come in our platform, Math Aspirants, and delivered a talk. Certainly in future, we will try to arrange some more theory sessions or other type of sessions with you, possibly in the nearby future itself. I expect your cooperation in that in future too. Thank you. Thank you very much. Please, one more thing, please do share the PDF of the notes if possible. We can share it with the recording. Okay.
Yes. So what where I was writing notes on a slide I have made. So initial part of my slides are slides for the series. So I'll share that also. So
Okay.
it's mainly slides, and then towards the end you will see the notes.
Okay. Yeah, it is anyway, it is only for their study purpose. So whether it is well organized or not, that doesn't make any problem. Okay. Because they will get some ideas while doing that. Actually, it is really difficult to take all the notes while attending online session. That's why we are trying to provide notes.
So I should have been slower.
Yeah, possibly. See, anyway, in the online mode, there are a lot of problems, difficulties will certainly be there. Maybe due to the network of the participants and all that will be there. Yeah, I think you are in a moderate speed, not that much high or not that much slow. I think there is nothing to change in your presentation style, I think. You have done in a great way. Thank you. Thank you
That's
very
the
much.
online challenge. Like in classroom, we can see the faces and understand where you need to slow and yes.
Yeah, it's actually very difficult to teach something by just looking at the laptop or a screen without seeing the faces of the students. Even though we compel them, they won't open their video. Many speakers will used to say, in the beginning will request the participants to keep the video on. They are feeling very bad while speaking by looking at a laptop and all that. But many people have many net issues and data problems, so they won't certainly they won't usually switch on the video possibly.
Maybe, sir, it would have been better if they would have asked their doubts in the problem itself, like.
Yeah, but many students, some students will used to ask that type of questions, and many have okay, as you know, students from Kerala or people certainly have a feel of whether my question was right or wrong. That type of feelings are
Yes. That is the first problem that we need to overcome.
We are actually
overcome once you have some amount of confidence also.
Actually,
confidence about something taught already. Yes, sir.
Actually, we are trying through these sessions to increase the confidence level of students as well. That's why many people are getting an opportunity to interact, to meet in person and speak with others. So that type of things we are promoting that type of interactions, and also peer group interactions also through our groups. So I think certainly slowly they will change. They will develop in a usual college atmosphere. They don't have that type of while in a premier institute, certainly they have a different culture. They used to ask questions and all that. But in rural college, I think we can't observe that type of things currently. So that's why maybe.
Yes.
Anyway, our platform provides, trying to provide the students such an opportunity to be in a class. I think today itself, we have participants from Jharkhand, Maharashtra, from West Bengal, from Andhra, from Karnataka. So I think they will get a different experience, and through this experience, certainly they will improve. I think.
Yes, definitely.
My initiative is for that.
Yes.
So I would like to thank all these resource persons because without their help I can't do that, because we are doing all these things without any fund or any type of, even we can't provide any certificate or any other valuable things for any resource person because as we are an informal group, there is no validity in that. So
yes.
So only because of their love towards the subject, that's why all these people like you are coming in, joining with us. So I'm very happy on that. Okay, let us hope that more our students will get admission to premier institutes.
Yes.
Okay, thank you, Saranya. Let us wind up here. Thank you. Bye.
Okay, bye. Yeah.